We left off in part 1 of the climate system talking about the hole in the ozone layer. I have a bit of a weird connection to this story in that I traveled down to Antarctica about 10 years ago. One of the places I visited, in this case on Christmas Day, was Vernadsky Station. Now, Vernadsky Station is the one Ukrainian research station in Antarctica. One of the neat things about it is that it was a British Antarctic station that was sold to the Ukrainians for, I believe, £1 sterling a couple of decades ago. So about $1.50 Canadian. And we visited on Christmas Day, which started out in a weird way for me. Traveling with the Geographic Explorer, I was dumped off on most locations first to do some reconnaissance, some penguin counting, and some rookery evaluation. And then some tourists would come on the island. So just prior to the tourists coming on the island, Christmas morning at about 6 a.m., I was walking across a sheet of ice that was covered with penguin poop, and I started to slide. And once you start sliding on greasy ice, there's no stopping you. So I went down in a heap on my back, to protect my camera, and I was covered with this stinky penguin poop all day. People were talking to me, "Hey, there's some stuff all over your back. What is that?" And I said, "It's guano." "Yeah, it looks like crap." "Yeah, that's guano. It's penguin poop." So I made a poop angel in the snow, which was reported by several people to be a body emerging from the ice. Not true. We eventually made it to Vernadsky Station in the afternoon. It was Christmas Day, but because it was a Ukrainian station and they were Orthodox, it wasn't Christmas Day for them. That was coming up January 7th. So we got to do a Christmas vodka shot in Antarctica, homemade by the scientists there. This is the station that, while the British were operating it, discovered the hole in the ozone layer, and this made global news. Ultimately, the world came together to solve this problem. The hole in the ozone was created by people. It was created by CFCs, chlorofluorocarbons, and they were used in everything from deodorant to hairspray to cleaning agents. They're used in refrigerators, radiators, all kinds of different devices, and once they get in the atmosphere, they stay there. While they're in the atmosphere, they destroy ozone. So this ozone has a very important function for us. It protects us from incoming ionizing radiation, high energy radiation. Without the ozone layer, we are exposed to much more radiation of the dangerous ionizing kind that damages our genetic code, leading to various cancers and other problems. PBS has a documentary on this. I'll try to figure out what it's called. Let's see. It's Ozone Hole, How We Saved the Planet. Tells the largely forgotten story of the hole in the ozone layer and how the nations of the world came together to fix it. So in that documentary, they interview Professor Mario Molina, who won the Nobel Prize for identifying the CFC problem. James Lovelock inspired Molina to take a look at the CFCs. Jonathan Shacklin, who discovered the ozone hole, and ultimately, this led in September 1987 to more than 30 countries agreeing to cut the use of CFCs. This was signed in what was called the Montreal Protocol, the world's first global treaty to reduce pollution. In 1990, Margaret Thatcher urged further support for the Montreal Protocol so that CFCs could be phased out completely, and importantly, developing nations could afford ozone-friendly technologies. So this worked, and ultimately, the ozone hole closed. Hasn't closed completely, hasn't closed permanently, but it's a lot smaller than it used to be. Now, if we take a look at the history of ozone hole sizes, we can see relative to North America, the size has changed considerably. And if we take a look further back into time to the 1970s, the very late 1970s, the change is even more considerable. Now, taking a look at another component of the climate system, we're going to focus on the hydrosphere for a few minutes. The hydrosphere is all liquid on, over, and under the Earth's surface. Most of it, practically all of it, is in the oceans. About 1% makes up lakes, rivers, and groundwater. This is the water that we have accessible to us for our personal use: drinking, bathing, cooking, industry, recreation, things of that nature. That's 1% of the total hydrosphere. The global ocean circulates by two major current systems. Continental water consists of lakes, rivers, and groundwater. The ocean contains about 1,350 million cubic kilometers, while about, again, 1% or 15 million cubic kilometers, again, that's available to us. However, although it's only 1% of the total hydrosphere, this 1% is very important as it influences the climate system and it moves weathered material into the oceans. It's a major mover and shaker in the Earth's system, and it turns out in the Earth's climate system. Importantly, water can hold much more heat than air, and therefore it's much more effective at transporting heat. We use water in a radiator system to heat a house because it's more effective than pumping hot, dry air through a house. Although pumping hot, dry air through a house is much less expensive, so that's the way most people go. Now, taking a look at the surface ocean currents, these are driven by wind, and we can see in the North Atlantic a clockwise gyre. The Gulf Stream would be represented by this northeasterly flow of water. This warm, salty water coming out of the Caribbean takes this Gulf Stream path up to high latitudes. And at these high latitudes, principally off the screen here, up here off of East Greenland, we have water cooling off, and because it's already saltier than the surrounding seawater, it becomes more dense than that surrounding seawater and it sinks. It has to be replaced by other water, which comes out of the tropics again. So this is our radiator heat system for the Atlantic Ocean region. Now, when we talk about ocean circulation in 3 dimensions, we use the term thermohaline ocean currents, or the thermohaline ocean circulation system. In this situation, cold, salty, deep water moves towards the equator. So we run warm, salty water to the high latitudes, more likely up here than here. It cools off, it sinks, and it's replaced by more warm, salty water. So that interplay here between the subtropics and the high latitudes heats up the high latitudes more than they would be without that current. This is why we can see palm trees in Iceland, palm trees all the way up here, again off the screen, in Tromsø and Hammerfest in Norway, and then off the coast of East Greenland. Okay, so this cold, salty, deep water is going to move towards the equator. It's going to pass the equator and join the Antarctic bottom water circulation system that circles Antarctica. Eventually, the water is going to upwell for one or more reasons that we'll talk about later on in Geology 206, and that brings it back full circle. The cryosphere, on the other hand, is the ice surface. It's the ice sphere. It consists of ice caps and glaciers, floating ice, sea ice, and frozen lakes and rivers that we're surrounded by here. This cryosphere is the ice component of the climate system. It's comprised of 33 million cubic kilometers of ice, mostly in the ice sheets of the polar regions. That means Antarctica and Greenland. They dominate the ice budget of the Earth. A little bit from Iceland and the ice caps there. Continental glaciers, on the other hand, cover about 10% of the land surface, holding about 75% of the world's fresh water. This is going to become more important as global warming scenarios begin to play out. The main role of the cryosphere, however, is to reflect most of the solar radiation that strikes it. This tends to keep the Earth cooler than it normally would be. Melting snow is the source of much of the fresh water in the hydrosphere. 60% to 70% of annual precipitation in the Sierra Nevada and Rocky Mountains comes as snowfall. And because those are relatively dry regions, that water is very important. The Sierra Nevada provide Napa Valley, the Great Valley of California that produces 3 crops per year with its needed water. Rocky Mountains supply farmland in the Front Range of Colorado and elsewhere along the Front Range. So let's take a look at where this ice sits. Sea ice is going to be forming, appearing and disappearing on water. Sea ice is ice that forms from seawater. It's not ice that's in the ocean or in the sea. It's ice that forms from seawater. Glaciers are going to take up much less space. They're going to form generally in mountainous regions. Ice sheets form in perpetually cold places, such as the Great Ice Sheet of Antarctica. It's not called that. It's called the Ice Sheet of Antarctica, or the Antarctic Ice Sheet. And the ice sheet that sits on top of Greenland, the world's largest island. Ice shelves are found adjacent to the ice sheets, and these can be relatively unstable. So the Ross Sea is a big ice shelf. If this is to decay, to break away, this is an enormous area that would then be exposed to incoming solar radiation. instead of reflecting it, it would be absorbed by this space here, the Ross Ice Shelf, that is larger than most countries. Continuous permafrost is hidden below the surface. Discontinuous permafrost also hidden below the surface. Here is a closer view of Antarctica. I've shown you some pictures from over here, Deception Island, the Antarctic Peninsula. That station that we looked at, Vernadsky, is located over here. And here we have the interface between the cryosphere and the hydrosphere. This is in the Antarctic Peninsula. This is a glacier that is calving into the Southern Ocean here. So the cryosphere meets the hydrosphere beneath the atmosphere. And another image here, also from the Antarctic Peninsula. Now we're going to move up to the other hemisphere, the northern hemisphere, and take a look at Greenland, some images from there. These are going to be from near Amashilik, and there's a little town called Kulusuk here. So here we have calving just north of Amashilik. This is in August. What you see out here in the sea, this ice that's in the sea, is not sea ice. These are icebergs. Berg means mountain, so mountain ice or ice mountains. These come from the calving of the glaciers off of the ice sheet of Greenland. So icebergs come from land, sea ice comes from the sea. Just another image here. Again, this is August, and we can see the ice sheet working its way into the North Atlantic. The East Greenland Current is just off the image here. So those images were taken from around here. Moving out into the North Atlantic, we're going to take a look at Iceland now. Here we have Iceland, an appropriate photo of Iceland. You can see clearly, I believe, the Vatnjokull, the big ice cap over the Vatn volcano. And you can see other volcanoes covered by smaller ice caps here. This would be considered an ice cap, ice cap, ice cap. This is Snæfell, located right here. And as I mentioned before, it's the gateway to hell. If you want to go to hell, this is the traditional route. You just walk up to the top here and take the escalator. The Icelanders take advantage of this situation, this icy situation, and the Vatnjokull by offering you the chance to experience new dimensions. One of the neat things about Iceland is they speak Icelandic, which is Old Norse, and they don't like to adopt modern words. So every word for every modern thing has an Icelandic equivalent. So here, a super jeep tour in Icelandic is the Jeppafjörður. The snow scooter tour, we call a snowmobile tour, would be the Velsledafjörður. Cross-country skiing, Gonguskabradjur. Gonguskabradjur. And snowmobile tours no longer available, so we won't talk about that. Or, for maximum laziness, you can take the Jökullarutan, the glacier bus. Here we have the snow scooter tour getting ready to begin. This is the Eastern Blue Lagoon, which is the cold Blue Lagoon. The Western Blue Lagoon is the hot Blue Lagoon. So here we can see the Vatnjokull calving off into this bay or lagoon, and you can see these stripes of rock, debris, sand, silt, clay, gravel, cobbles, pebbles embedded in the ice here as these black bands. These fall out when the ice melts. So this is known as ice-rafted debris. Debris that is rafted out into the water with ice. A closer image of the Vatnjokull here calving. And what you can see here in the forefront is a terminal moraine that is becoming vegetated. As a climate scientist, what this means is the glacier no longer reaches this spot. It is terminated before it gets to this rock pile. So it's in retreat. It's getting smaller. Now, taking a look further to the north in Svalbard, this is the Austfonna ice sheet, a large northern hemisphere ice sheet. You can see its terminus here, and a little closer view here. Here we have the hydrosphere, fresh water pouring off from the cryosphere into the ocean. So all hydrosphere here with some ducks flying through the atmosphere. Now, the sea ice variability is becoming increasingly important in climate models, and therefore increasingly important for us, for our survival as a species and our success as a species. Sea ice has been decreasing dramatically to the point that soon, we believe, there will be an opening through the Arctic islands that can be used for transportation from Europe directly to Asia, cutting out the Panama Canal and all the hassles of dealing with that and the great distance that's required to go that direction. So here, take a shortcut. Seems like a great deal, except there are already lawyers jumping from every country in the Northern Hemisphere into the game here. Who will be responsible for cleaning up the first major incident here in the Arctic? These are the Canadian Arctic Islands. So Canada has an obvious interest in this. They don't want people coming through without paying. They don't want people wrecking their vessels in here and then leaving the scene of the accident. Further to the south, this is a shot from right around the border of the Yukon and Alaska on the Alcan Highway. And we can see some mountain glaciers in this image. So the sea ice is decaying at a faster rate than it's reforming. And again, sea ice forms in the sea. We freeze seawater. When you freeze seawater, you tend to exclude the salt. Sea ice still has some salt in it, but not as much as seawater. That means there's extra dense salty water forming at the same time as sea ice forms, and that water sinks rapidly.